AC voltage applied to a series LCR circuit. A series LCR circuit is connected to an AC source. The resistor, inductor, and capacitor are in series. Voltage of the source be V is equal to Vm sine omega t. If Q is the charge on the capacitor and I be the current at time t, we have from Kirchhoff's loop rule L di by dt plus IR plus Q by C is equal to V. Equation 1. Now we solve this equation to determine the instantaneous current I and its phase relationship to the applied alternating voltage V. We use the technique of phasors. Phasor diagram solution. Since the resistor, inductor and capacitor are in series, therefore, the AC current in each element is the same at any time, having the same amplitude and phase. Let it be I is equal to Im sine omega t plus phi, equation 2, where phi is the phase difference between the voltage across the source and the current in the circuit. Let I be the phasor representing the current in the circuit as given by equation 1. Let VL, VR, VC and V represent the voltage across the inductor, resistor, capacitor and the source respectively. The instantaneous voltage across a pure resistor, VR, is in phase with the current. The instantaneous voltage across a pure inductor, VL, leads the current by pi by 2. The instantaneous voltage across a pure capacitor, VC, lags the current by pi by 2. Therefore, VL and VC are 180 degree out of phase and in opposition to each other. This means that we cannot simply add together VR, VL and VC to find the supply voltage. The lengths of these phasors represent the amplitudes of VR, VC and VL. VRM is equal to IMR, VCM is equal to IMXC, VLM is equal to IMXL. Equation 3. The voltage equation for the circuit can be written as VL plus VR plus VC is equal to V. Equation 4. Since VC and VL are always along the same line and in opposite directions, they can be combined into a single phasor, VC plus VL, which has a magnitude VCM minus VLM. Since V is the hypotenuse of a right triangle whose sides are VR and VC plus VL, using Pythagoras theorem we get Vm square equals to Vrm square plus Vcm minus Vlm whole square is equal to Imr whole square plus Imxc minus Imxl whole square. Vm square equals to Im square plus r square plus xc minus xl whole square. Im square is equal to Vm by square root r square plus xc minus xl whole square. Equation 5. The term square root r square plus xc minus xl whole square is equivalent to the resistance in a circuit. We call it the impedance Z in an AC circuit. Z is equal to square root r square plus xc minus xl whole square, equation 6. The phase angle phi between VR and V and can be found. We have tan phi is equal to VCM minus VLM by VRM. Using equation 3, we get tan phi is equal to XC minus XL by R, equation 7. Equations 6 and 7 are graphically shown in the right triangle with Z as its hypotenuse. This is called impedance diagram. For amplitude of current, we have Im is equal to Vm by square root r square plus xc minus xl whole square. Now we shall see how the circuit behaves for different values of xc and xl. Case 1. xc is greater than xl. xc minus xl is positive. Therefore, phi is positive and the circuit is on the whole capacitive. Therefore, the current in the circuit leads the source voltage. Case 2. xc is less than xl. xc minus xl is negative. Therefore, phi is negative and the circuit is predominantly inductive. Consequently, the current in the circuit lags the source voltage. Case 3. xc is equal to xl. xc minus xl is equal to 0. Therefore, phi is 0 and the circuit is purely ohmic and the impedance is minimum. Here we have a phasor diagram and variation of V and I with omega t for the case xc greater than xl. Thus, we have obtained the amplitude and phase of current for an LCR series circuit using the technique of phasors. Resonance. An interesting characteristic of the series RLC circuit is phenomenon of resonance. The phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. The frequency is called the system's natural frequency. The impedance Z of RLC series circuit is given by equation Z is equal to square root R square plus XC minus XL whole square. Equation 8. Let when omega is equal to omega naught, XC is equal to XL, the impedance of circuit is minimum. Z is equal to R. 1 by omega naught C equals to omega naught L. Omega naught equals to 1 by square root LC. Equation 9. Omega naught is called the resonant, the frequency. At resonant frequency, the current amplitude is maximum. Im is equal to Vm by R. It is important to note that resonance phenomenon is exhibited by a circuit only if both L and C are present in the circuit. The total source voltage appears across R. Vm is equal to IMR. Resonant circuits have many applications. For example, in the tuning mechanism of a radio or a TV set. While tuning, we vary the capacitance of a capacitor in the tuning circuit such that the resonant frequency omega naught is equal to 1 by square root LC of the circuit becomes nearly equal to the frequency of the radio signal to be received. When this happens, the amplitude of the current with the frequency of the signal of the particular radio station in the circuit becomes maximum. Sharpness of resonance. The amplitude of the current in the series LCR circuit is given by Im is equal to Vm by square root R square plus Xc minus XL whole square. Im is maximum when omega naught is equal to 1 by square root LC. Im maximum is equal to Vm by R. For other values of omega, the amplitude of the current is less than the maximum value. Suppose we choose a value of omega for which the current amplitude is 1 by square root 2 times its maximum value. At this value, the power dissipated by the circuit becomes half. From the curve in figure, we find that there are two such values of omega, say omega 1 and omega 2, one smaller and the other greater than omega naught and symmetrical about omega naught. Thus we can write omega 2 is equal to omega naught plus delta omega. Omega 1 is equal to omega naught minus delta omega. The difference omega 1 minus omega 2 is equal to 2 delta omega is called bandwidth of the circuit. The quantity omega naught by 2 delta omega is regarded as a measure of the sharpness of resonance. The smaller the delta omega, the sharper or narrower is the resonance. The sharpness of resonance is given by omega naught by 2 delta omega is equal to omega naught L by R. Equation 10. Omega naught L by R is also called the quality factor Q of the circuit. The Q, quality factor of a resonant circuit, is a measure of the quality of a resonant circuit. Larger the value of Q, the smaller is the value of omega 2 minus omega 1 is equal to 2 delta omega, or the bandwidth, and harper is the resonance.